Here we discuss about the paper titled Inconsistency in the Application of Adiabatic Theorem. The authors have showed that the adiabatic theorem is problematic if the change in the eigenstate is significant, irrespective of how closely the requirement of adiabaticity is satisfied. An example of a two-level system is demonstrated to show the inapplicability of adiabatic theorem even though Hamiltonian varies slowly. So let's start. Consider the initial state of the system as one of the eigenstates of the initial Hamiltonian. The system evolves under a unitary operator. The time dependent Hamiltonian is related to the unitary operator such that the state of the system satisfies the Schrodinger wave equation. So the general state of the system will be the linear combination of the eigenstates of the Hamiltonian at that time, and we have the coefficients attached to it. Since it is an ansatz, we substitute in the Schrodinger wave equation and we get the differential equation as equation 1. So the adiabatic theorem requires equation 2 to be satisfied. So then the transitions to the other levels are supposed to be negligible due to the rapid oscillation arising from the phase factor. So this that gives the solution as equation 3. So I have done a video on adiabatic approximation. You can look into it. So to how to get the equation 3 as the solution of the Schrodinger wave equation. So in this paper, so they showed the solution is inconsistent. So let's look at the details. So they have considered the state psi bar, which is nothing but u dagger E naught. And under adiabatic approximation, this psi bar turns out to be equation 4. This equation 4 satisfies the Schrodinger wave equation with a Hamiltonian h bar. And with this result, what we get here is that this inner product u dagger with the initial eigenstate, this must be 1 because it's a unitary operator. You will get identity here. Under the adiabatic approximation, this is not equal to 1, which is false because it should be 1. So this is the inconsistency, and this inconsistency is clearly because of neglecting the deviations from the exact time evolution. And however, evolution is not infinitesimally slow, so and neglect of the extra terms, that the exact terms, leads to the inconsistency. So to elucidate this point, we define a new unitary transformation, and it is equal. This unitary transformation gives the exact adiabatic solution what we have seen in equation 3. So one can find the corresponding Hamiltonian to this unitary transformation. In this Hamiltonian, the transition matrix elements between the different initial eigenstates, they are not rapidly oscillating anymore, right? Here we have the coefficients attached to it in between the two eigenstates, so therefore they cannot be neglected. However, the adiabatic theorem says these terms should be neglected. Thus the adiabatic theorem leads to inconsistency, regardless how slowly Hamiltonian changes. So we'll see that through an example here. So consider a two-level system with exact time evolution defined by with exact time evolution unitary operator defined by equation 10, with theta is equal to omega naught t, and the unit operator which is defined by cos 2 pi by 2 pi t by tau, 2 pi t by tau, sin 2 pi t by tau comma 0. So from this one can associate the Hamiltonian associated Hamiltonian can be calculated. So it is easy to show that the evolution operator satisfies the adiabatic theorem as long as the vector n changes slowly compared to omega naught. The time scale tau corresponds to large time scale. Now consider the projection operators of the eigenstates. If we consider the projection operator, and if we consider at a projection operator at a particular time is equal to tau by 2, so what we should get from the adiabatic theorem is that the u acts on the initial projection operator and u dagger, you should get the eigenstate at later instant of time. This is the one which we should get under adiabatic approximation. But what we are exactly getting is when u of t acts on this projection operator, you will exactly get p of plus of t. That p of plus of t is nothing but p of minus of 0. So the eigenstates have the eigenstate p plus of 0 get converted to p of minus of 0. This shows that the eigenstate the adiabatic theorem is invalid because it has gone from one eigenstate to the other eigenstate. Okay, so this inconsistency one can quantify it by deriving by finding a quantity called given here as q. So this quantity can tell you when the adiabatic theorem is bound to fail. If it deviates from 1, then we can say the adiabatic theorem is invalid. Okay, for two-level system, q can be expressed like in equation 15. So one can also show that through numerically solving the Schrodinger wave equation and calculate the fidelity. So how it deviates from the eigenstate from the initial eigenstate as the input, and one can solve the numerically and also show that the fidelity it was 1 in the initial time, and it goes to almost 0 and then it comes back. So here we can see that the adiabatic theorem is invalid at this particular instant of time. Okay, thank you. That's all the important results of this paper.